Dear students, today we discuss how to make inferences about population standard deviations. We know that standard deviation is a measure of spread or variation of a data set. The sample standard deviation is given as S is equal to root of sigma xi minus x bar square by n minus 1. If a data set has high variation, its standard deviation will be very high. On the other hand, if a data set has low variation, its standard deviation will be low. A data set with no variation at all will have zero standard deviation. Now remember this, for a variable x, the standard deviation for all the possible values of x, or the standard deviation for the entire population, is known as population standard deviation, and it is denoted as sigma, and population variance is sigma square. That is the standard deviation for the entire population. And as in the case of mean, proportion, etc., the entire population is unknown. So we have to make an inference about population standard deviation, population variance, etc., using sample variance S square and sample standard deviation S. So in this session and in the subsequent sessions, we will discuss how to conduct hypothesis tests about population standard deviation, and also how to construct confidence intervals for population standard deviations. Now, hypothesis testing for population standard deviation is based on a distribution called chi-square distribution. Chi-square. We read it as chi-square, we write it as chi-square distribution. Remember this, estimators are not directly used for hypothesis testing. Using the estimators, we develop a test statistics. To test the significance of a mean or the difference between means, we used Z and T, and Z was used to test the significance of a population proportion. So Z, T, etc. are test statistics. Similarly, to test the significance of population standard deviation, we use the distribution known as chi-square distribution. So in this session we will define what is a chi-square distribution. We also consider its properties. Now, a variable is said to have chi-square distribution. A variable is said to have chi-square distribution if its distribution has the shape of a special type of right skewed curve called chi-square curve. A variable is said to have chi-square distribution if it has a shape or if its shape is a typical right skewed shape, and this distribution is, that is, this curve is known as chi-square curve. So, as a definition, a variable is said to have a chi-square distribution if its distribution has shape of a special type of right skewed curve called chi-square curve. Now, there are an infinite number of chi-square curves and chi-square distributions. Like a T distribution, there are infinite number of chi-square distributions. There is only one Z distribution, remember that. So, we identify a chi-square distribution with its degrees of freedom. We identify a chi-square distribution with its degrees of freedom. That is, like the T distribution, chi-square distribution also depends on what is known as the degrees of freedom. Now, let me draw a typical chi-square distribution. This is chi-square. This is f of chi-square. Now, it is a squared quantity, so naturally it starts from 0 and it is right skewed like this depending on the degrees of freedom. So, the distribution is something like this. Now, so these are various chi-square curves for degrees of freedom 5, for degrees of freedom 10, for degrees of freedom 20, etc. Now let me say what are the properties. The area under chi-square curve is 1. Like a T distribution, like a Z distribution, area under chi-square distribution is 1. And a second property is a chi-square curve starts at 0. A chi-square curve starts at 0 and extends indefinitely to the right. Extends indefinitely to the right, approaching but never touching the horizontal axis. Approaching but never touching the horizontal axis. It starts at 0. The third property is it is right skewed. It is right skewed. And the last property, as you can see, as the degrees of freedom increases, this chi-square distribution approximates a normal distribution. For small degrees of freedom, it is highly skewed. As degrees of freedom increases, as you can see here, it is something like a normal distribution. So, as degrees of freedom increases, chi-square distribution approximates a normal curve. And remember these properties of chi-square distribution. And chi-square distribution is used for testing hypotheses about population standard deviations. Now, for performing a hypothesis test, or constructing a confidence interval for a population standard deviation, we have to find how to calculate the area under chi-square curve. We have to study how to calculate the area under the chi-square distribution, just as the case of T distribution and Z distribution. We know that in the case of Z distribution, 95% of the area lie between minus 1.96 and 1.96. For the T distribution, this area depends on the degrees of freedom. For example, for 20 degrees of freedom, 95% of T lie between minus 2.038 and plus 2.038. Like that. In the same way, for constructing confidence intervals and also for performing hypothesis tests for population standard deviation, we must know how to calculate area under chi-square distribution. Now, chi-square alpha, consider this chi-square alpha denotes chi-square value having area alpha to its right under the normal curve. Alpha is 5%, 10%. So chi-square alpha means an area equal to alpha to the right of chi-square alpha. Now, so in every books of statistics, you will see you will see there is a table of chi-square values, and in the column headings you have various values of chi-square alpha. As an example, chi-square 0.995, chi-square 0.995 as an example. So it shows 99.5% of chi-square value lie to the right of 0.995. Now let us see an example. So in this way we can find out the various values of chi-square, and as an example, for a chi-square curve with 12 degrees of freedom, chi-square with degrees of freedom is equal to 12 degrees of freedom. The chi-square value, chi-square 0.025, chi-square 0.025, that is area, that is the value of chi-square having an area 0.025 to the right for 12 degrees of freedom. This value is 23.337. It means 95% of chi-square value will be between 0 and 23.337 for 12 degrees of freedom. Similarly, for 7 degrees of freedom, chi-square degrees of freedom is equal to 7. As an example, these are all given in the table. For 7 degrees of freedom, having an area 0.05, to the left, like this. That is, this is 0.05 to the left. And as we know that, as the total area under chi-square is equal to 1, the area to the left is 1 minus 0.05 is equal to 0.95. From the table, you will get it as 2.167. So, 95% of chi-square is above 2.167, 5% is less than 2.167. Another example is chi-square with the value for 20 degrees of freedom, chi-square 0.05. It divided 95 into 2, that is chi-square. That is two areas, 0.025. Here it is 0.025, that is 95%, 0.95, that area. So, for 20 degrees of freedom is equal to 20, area to the right is equal to 170. That is 97.5% is below 34.170, and this is 1 minus 0.025. 1 minus 0.025 is equal to 0.975. That chi-square value is 9.591. 9.591. So, 95% of chi-square value is between 9.5 and 34.17. So, in this way, you can calculate all the chi-square values from the table, but softwares will give you the values directly. So, we use this chi-square distribution for testing the significance of one population variance or one population standard deviation. We also use this for constructing confidence intervals.